Hey chemists, I wanted to go through these notes about how the periodic table can connect to understanding the reactivity of the elements so that we had this as a reference to look back at later. We could really make the connection from what we learned about atoms to electrons all the way to the bonding and the reactivity that we're going to see. So I'll click back and forth through several things here where we are looking at the notes we'll fill in. We'll look at the filled in versions, but we'll also have the periodic table handy that we can look at any and all of these times. So as you go through any notes, as you go through any worksheets or any learning activities in mastering chemistry, you always have to have the periodic table with you, and you should always have it labeled across the top with what we know about the valence electrons: 1, 2, 3, 4, 5, 6, 7, and 8, and also what we know about the ionic charges: +1, +2. These guys right here in the middle we know can change, so we have to have a Roman numeral with those. +3. Right here we're more often +4 than -4, but -3, -2, -1, and then our noble gases are 0. So I wanted to throw that out there because that, even though we aren't necessarily using those details to answer all of these questions, it connects very, very much. So right here, we've got just a small chunk of the periodic table in the form of Bohr models. We could do the same thing with electron configurations to know this, but the real key is understanding how our protons, which is our atomic number, connects to the attraction that it has for the electrons, and even more importantly, how many valence electrons we have which feel that attraction. So in previous units and previous chapters, we've already defined these patterns. The effective nuclear charge, which is what we call Zeph, is how much positive charge those valence electrons are able to feel. We could see as we go across here in green, we have a pattern. It goes up 1, 2, 3, 4, 5, 6, 7, and 8. That's the exact same pattern that we could expect for our valence electrons. How many electrons are in that outermost level and those sets of sublevels that are farthest from the nucleus? But if we looked at lithium down to sodium, here to potassium, and even further down this column, we would see that we're adding more levels, we're adding more inner electrons, we're adding more sublevels, but we end up with the same Zeph, or that same leftover charge on our attractions, or excuse me, on our valence electrons. So we can check the definition, but the pattern left to right, it goes up, but top to bottom, it goes down. The higher our effective nuclear charge, that turns into a bigger, stronger attraction. So as I pop up there, we see the definition, we see the pattern, we see the trend, and then we see that more Zeph attracts and holds those electrons even harder. Shielding, and I've got it here, but I'm going to slide back over so that you can listen, and you can even go back to your Unit 2 definition sheet, your Unit 2 notes. Shielding is these electrons that we're circling in red. How many electrons are in our inner levels? And we could even break that down to the S, the P sublevels that are inside. Well, as we go across a row, we are adding electrons to the outermost level. We're not changing how many level 1 or level 2 electrons there are. We're adding them to that outermost level. So across a row, left to right, we would see that it says the same: 10, 10, 10, 10, 10. And we got that pattern down really well in our electron unit, but we're coming back to that because that applies here. But each time we add another row, we are adding more electrons, and specifically more shielding electrons, or that extra row is an extra energy level. So once again, we see a pattern. Each time we go down, all of the electrons that could be represented by that noble gas notation are the inner electrons, the core electrons, or the phrase we use is our shielding electrons. So the shielding is how many inner electrons are there, and really the blocking that comes from those. Left to right, we don't see a change. Top to bottom, we do. And that would make, when we have more shielding, that means we have less attraction. There's more stuff in the way. Between that positive and that negative, we've got blocking and repulsion that's happening. So we'll click over in a minute to see all of that filled in, but that's important because those two trends together, and we need both of those things to understand how big our atom is. But the radius is just that distance from our positive central nucleus all the way out to those outermost valence electrons. How far is that? And we see that as we go further to the right and we put more Zeph on there, it pulls it in closer because of more attraction. As we go top to bottom and we add those more levels there, it allows that distance to be greater because of decreased attraction. So the radius is not really the thing causing the attraction, it's a result of it. When we have a strong attraction, when things are very close to one another, that's when we have a very small radius. And when they get a little bit further, we have a larger radius. So that's what we have right there. The distance, we see patterns, and really we want to be able to apply any and all of this to a blank periodic table on test day. And if this isn't already on our periodic tables, we need to write this on there and keep this on there. Find a blank periodic table, ask your teacher for a new copy, look for a new copy in the room, and write this stuff on there. So once again, far to the right is a high Zeph, high valence electrons, high attraction, which makes our atoms more likely to be small. Close to the bottom is high shielding. Lots of levels, lots of distance, and it makes our atoms very, very large. So over here, francium has the most shielding and the least Zeph, making it the biggest. And over here, helium has the least shielding, and it's among the highest in terms of the Zeph, so it's the smallest atom. So I wanted to just really quick have this first video as a recap so that those fundamental explanations can really click and make sense before we use them to explain our next topic.